Hello students, welcome to EPG Pathshala. I am Dr. Aranya Bhattacharjee from the School of Physical Sciences, Jawaharlal Nehru University. Today we are going to discuss about a very interesting module on electrons in periodic solids 1, which comes under the paper Solid State Physics. So the learning outcomes is something like this, that after studying this module you shall be able to first learn about the dominant role of electrons that play for determining the physical properties of solids. You should also learn about two broad categories of electrons. One, those which remain localized and form part of the ions, and those for which wave functions change considerably in the solid. The later category, that is those for which the wave functions change considerably in the solids, determine the large measure the characteristic properties of the solid. Also, you will know about one, the macroscopic crystal possesses discrete translational symmetry in the bulk. Second, simultaneous eigenstates of the Hamiltonian and the translational operators using the periodic boundary conditions. And a very important concept that you will learn, the Bloch theorem, which is a very general and important property of energy eigenfunctions in crystals. And finally, we will also set up the solution of Schrödinger equation by an expansion in terms of plane waves and show how we can again derive the Bloch theorem from a very general consideration. Now you see that the subject of solid state physics introduces the concept of generation of macroscopic or large scale characteristics from the microscopic or the small scale characteristics of the solid materials. That is, it relates the large scale characteristics to the atomic scale of these materials. Now, solid state physics can't be studied without adequate knowledge of quantum mechanics, electromagnetism, metallurgy, etc. So, this module is essential as it frames the very basic concepts that will be used throughout for the study of this subject, especially the electrons in solid and their role. So, this slide actually discusses briefly the importance of the quantum behavior of electrons. Now, as you can see from this figure, there are a lot of properties which actually depends upon the quantum behavior of electrons. So, on the left hand side, as you can see, that physical properties like the lattice vibrations, for example, can be influenced by the nature of the electrons. And then you have the chemical properties, electrical properties, for example, the conduction. On the right hand side, you have the thermal properties like the specific heat, magnetic properties, and the optical properties. So all this put together, you can say that the quantum behavior of electron influences most of the properties of the crystal or the solid that we take into consideration. All physical and chemical properties of solids are ultimately linked to the quantum behavior of electrons and in a small measure of to ions. The nature of eigenfunctions and eigenenergies of electrons play a crucial and dominant role in our understanding of most of the properties of solid. For example, the strength and nature of binding between atoms depend very much on how the wave functions of the electrons behave as the atoms come close together to form a solid. To illustrate this statement, it is instructive to recall the way two hydrogen atoms bind to form a molecule. As the atoms come close, the wave functions of the two electrons change by expanding into the intervening region, which has lower potential energy. The expansion of the wave functions also lowers the kinetic energy, as the kinetic energy is related to the gradient of the wave function, which gets reduced as the wave function spreads. Thereby, at some distance between the atoms, the overall energy is lowered. This leads to the formation of bound state, which has lower energy than the free atoms. Transparency of a solid to light of frequency nu similarly depends upon whether the electron ion system can absorb the corresponding photon or not. This in turn depends on whether electronic energy levels with a spacing h cross nu are present in the solid. The ordinary glass is transparent because its energy levels have a gap larger than the photon energies in the visible range. In the similar manner, characteristics of other optical properties, electrical properties, thermal properties, magnetic properties, etc., all have their basic origin in the quantum states and eigenenergies of electrons and ions. So, what is a macroscopic solid? The number of electrons and nuclei in a macroscopic solid is enormously large, of the order of Avogadro number. In principle, any property of the solid is a result of the collective behavior of these particles, which are strongly interacting. Clearly, a straightforward approach to solve Schrödinger equation for such a system is an impossible and futile task. Yet, an enormous amount of progress has been made in our understanding of solids in the past 100 years or so. This had been achieved through a number of experimental inputs and theoretical procedures. A very important aspect has been the physical insights obtained through solving simple and often ideal problems. Quite often, in order to understand a particular phenomenon, one aspect of the underlying physics plays a very dominant role. So, its identification and modeling proves very fruitful for understanding the phenomenon. Electrons behave in diverse ways. Consider, for example, the sodium metal and imagine its formation as the atoms are brought closer. At the order of separations where binding occurs, where tens of the 11 electrons of each atom, which are in closed shells, are only weakly affected, but the quantum state of the one electron in the 3s state is drastically affected. This state feels the potential of the neighboring atoms and the wave functions of all such electrons spread throughout the crystal. They can be loosely regarded as free and are responsible for the metallic conduction. Of course, this happens as the extended wave function of the 3s electrons lowers the energy for the whole set of atoms, thus providing a binding glue. The other bound electrons play the role of providing the effective potential for the extended electrons. On the other hand, for the sodium chloride crystal, the 3s electrons of the sodium atoms transfer to 3p shell of chlorine atoms, thereby forming positive and negative ions with closed shells. This process lowers ionic energies, and charged ion bind through electrostatic forces to form a regular crystal, which is an example of ionic crystal. For group elements like carbon and silicon, the crystal has a diamond structure in which each atom has 4 neighbors in tetrahedral environment. Here one thinks of 4 covalent bonds for each atom, in which 2 electrons, one from each neighbor, pairs up. This means that the density of electrons along the line joining the neighbors is high and is lower in the intervening space. Again, a set of electrons spread their wave functions but in a more inhomogeneous manner to form relatively localized bonds. To illustrate these points, we include 2 figures exhibiting electron charge densities for 2 solids. One is for copper, the other is for silicon. These are colored contour maps in certain plane of the crystal. The colors give an idea about the charge density in the planar region according to the color provided with the figures. The lines are contours on which the charge density has a constant value. These plots have been made using advanced numerical codes which implement a method known as the density functional theory. For copper, one notes that apart from the small neighborhood around each atom, the density has a fixed value, that is the blue color. Now, around each atom, the red, one clearly sees a shell structure with empty regions and some thin shells of higher density. There are 3 lobes of high density which reflect the 3 covalent bonds in the plane. In the intervening regions, one has large depletion of charge and much variation. In order to understand this complex behavior, one needs to proceed in steps. The first step is to understand the eigenstates and the eigenenergy of a single electron in a periodic potential provided by the stationary ions arranged in periodic lattices. The justification for this step regarding ions as static is not straightforward. We will give some arguments regarding this in the later module, which deals with the dynamics of ions. But it will soon become clear that this step becomes an important input for looking at several aspects of the physics of crystals. What is generally true for all solids is that the electrons can be divided into two categories. The first category is those that remain bound to their respective atoms and form part of the ions. Their energies and wave functions change little from the atomic state. The second category of electrons is the valence electrons, whose eigenenergies and wave functions change considerably. These electrons are responsible for binding the solid and have a dominant role in giving solids their characteristic properties. One can already note exceptions like ionic solids. Quantum states of a single electron in a crystal. In this section, we look at the quantum problem of a single electron in a periodic lattice. Now, at each point vector Rn of the lattice, there is an ion providing a potential of the form V vector R small r minus vector Rn for the electron at position R. This gives rise to a total potential capital Vr, where n runs over all points of the lattice. Now we are in a position we can set up the stationary Schrodinger equation for an electron in this potential. That is, h multiplied by the wave function is equal to minus h cross by 2m del square plus v total multiplied by the wave function is equal to e as a function of r. This is an eigenvalue equation, and to solve it we need to specify the boundary conditions which occur at the boundaries of the crystal. A macroscopic crystal contains an enormous large number of atoms which are on a periodic lattice in the bulk, but the system cannot be regarded to have periodic translational symmetry due to its finite size. Only for the ideal situation of an infinite lattice the crystal potential and Hamiltonian have periodicity of the lattice, that is, V capital V as a function of vector r is equal to small v r plus rk, and also the Hamiltonian h as a function of small r vector r is equal to h small r plus rk. So that is, we simply saying that both the potential as well as the Hamiltonian is periodic in any lattice vector, that is rk. In mathematical terms, periodic boundary conditions, in the short form it is called PBC, imply the following conditions on the eigenfunctions. It's xi r plus n1 a1 is equal to xi r plus n2 a2 is equal to xi r, and similarly xi r n3 a3 is equal to xi r, which is simply showing that these wave functions are periodic with respect to n1 a1, n2 a2 and n3 a3. Mathematically and conceptually, it is extremely convenient to deal with periodic systems so that one can take advantage of the translational symmetry. For this purpose, one introduces a periodic boundary condition. Now, suppose the unit cell of the crystal is defined by the vectors a1, a2, a3, and the crystal is a parallelepiped with sides n1, a1, n2, a2, and n3, a3. Then it contains an integral number n is equal to n1, n2, n3 of cells. Now we extend our ideas about the periodic boundary condition. So what we do is now that we fold the crystal so that the opposite parallel faces of the parallelepiped are joined, much like a torus formed from a rectangle. This object has no surfaces and has translational invariance, as all lattice points are equivalent. These boundary conditions, known as the periodic boundary conditions, seem highly unphysical. But for macroscopic crystals, which are enormously large on the atomic length scale, these boundary conditions affect bulk behavior only minimally at the order of the higher order of n raised to power minus half. Admittedly, it cannot describe surface properties and surface effects associated with the crystal. Since our Schrödinger equation has discrete translational symmetry by virtue of the boundary conditions, we can greatly simplify its solutions by exploring this symmetry. This is done by choosing the eigenfunction to be simultaneous eigenfunctions of the translational operators and the Hamiltonian. So let T of RL denote the operation for a translation through a lattice vector RL. Its operation is defined as TRL acts on a function FR, and this function f as FR becomes FR plus RL. Clearly, all such operations commute with the Hamiltonian, that is, TRLH is equal to HTRL. We proceed by determining the eigenfunctions of T operators first. For this purpose, one notes that TRL for all lattice translation commute with each other and have the property TRL TR1 into TR2 is equal to TR2 into TR1, which can also be equal to TR1 plus R2. These properties enable us to find the simultaneous eigenfunctions and eigenvalues of the operators easily. Let the eigenvalue equation be TRL is applied on a function GR, which results in alpha RL multiplied by GR. Clearly, a function with the periodicity of the lattice UR equal to UR plus RL is an eigenfunction with eigenvalue unity. But there are other possibilities. So like this, that you have two translational vectors TR1, TR2 acts simultaneously one after the other on the function GR, which yields alpha R1 multiplied by alpha R2 into GR, which can be rewritten as alpha of R1 plus R2 into GR. Of course, now this basically follows from the previous properties of the lattice translational vectors. Thus, eigenvalues satisfy the relation alpha R1 into alpha R2 is equal to alpha R1 plus R2, whose possible solution is only that alpha R1 is equal to e raised to power I k R1, or in a very general sense you could say that alpha RL is equal to e raised to power I k into RL. Now, this form of alpha is chosen as the operators TRL are unitary, and hence the magnitude of their eigenvalues must be unity, which will be true if k is a real vector. The vector k characterizes the eigenstate of the translational operators. Because of the periodic boundary conditions, positions RL plus N1 A1, RL plus N2 A2, and RL plus N3 A3 are taken to be identical. This implies that T N1 A1 is equal to T N2 A2 is equal to T N3 A3 is equal to 1. Since the eigenvalue of the unit operator is 1, this puts the following restrictions on K, that is N1 K dot A1 is equal to 2 pi small n1, N2 K dot A2 is equal to 2 pi n2, N3 K dot A3 is equal to 2 pi n3, where all the small n's are integers. The solution for these relations can be written in terms of the basic reciprocal lattice vectors as k, vector k is equal to small n1 divided by capital N1 into the vector b1 plus small n2 divided by capital N2 into the vector b2 plus small n3 divided by capital N3 into the vector b3. The corresponding eigenfunctions are easily constructed. As may be verified, these have the form g kr is equal to e raised to power iota k dot r multiplied by ur, where ur is a periodic function with periodicity of the lattice. The presence of ur is the crucial difference for eigenfunctions between discrete translational symmetry and full translational symmetry. Now requiring the eigenfunctions of the Hamiltonian to be also the eigenfunctions of the translational operators implies the property that the TRL, when it acts on the wave function, it simply gives you a new wave function, but with the fact that this now is a function of small r vector small r plus the vector RL, and immediately this gives you e raised to power I k dot RL into the same wave function, which is basically now follows from the periodicity of the wave function. These eigenfunctions are, which we have discussed previous slide, are labeled by the vector k, which should be regarded as a conserved quantum number arising due to the translational symmetry. For each k, there are many energy eigenstates, as will be shown in the following, which we label as xi as a function of n and k. Using the explicit form which we had described earlier, one can write the eigenfunctions in the form as given in this equation. That is, the xi n kr is equal to e raised to power I kr into u. With the periodic function, this xi n kr depends on n and k. Now remember that this is actually called the Bloch's theorem after its discoverer Felix Bloch, who discovered it in 1928. This is a very important physical implication. It implies that the eigenstates are wave-like and extended throughout the crystal. The equation given in this slide relates the wave function in one cell to the wave function in all other cells. They just differ by a phase factor. This equation also shows that the solutions are complex plane waves modulated by the periodic function. This should be contrasted with the system with full translational symmetry, in which the eigenfunctions are just complex waves. The additional factor of u in the consequence is a consequence of discrete translational symmetry. However, while h cross k is conserved, it is not the momentum of the particle as in a system with full translational symmetry. One can easily check that the wave function in this given slide is not eigenstate of the momentum operator minus iota h cross del. Another very important technical point that follows is that about the number of allowed k values. We can take k values confined to one cell of the reciprocal lattice. To understand this, suppose we take this cell to be the Wigner-Zeit cell around k equal to 0. If we now add a vector g, the eigenvalues of the translational operator becomes alpha, which is equal to e raised to power iota k plus g dot Rn, which again becomes equal to e raised to power I k dot Rn as before. So we see that the eigenvalues do not change as g dot Rn is multiples of 2 pi. Thus, k values need to be taken from just one cell of the reciprocal lattice. According to this convention and convenience, this cell is the first Brillouin zone, which is the name given to the Wigner-Zeit cell around k equal to 0. Now to determine the number of allowed k values, consider the one-dimensional case first. Here, k equal to 2 pi m divided by n1a. So the distinct values confined to one reciprocal lattice cell, say that k lies between 0 and 2 pi a, are obtained by m equal to 0, 1, 2, 3 till ni minus 1, which are the n1 values. In higher dimensions, one uses the same logic for each direction to see that the total allowed k values are n equal to n1, n2 into n3. Since a Brillouin zone has the same area, the allowed values in the Brillouin zone are also n. So briefly we can conclude that what we know about the wave function of a particle in a crystal. So this is basically found out by the direct solution of the Schrödinger equation using momentum representation, taking into account the translational symmetry of the crystal. The direct solution of the Schrödinger equation. So far, the conclusions about the wave function of the particle in a crystal are derived from the translational symmetry of the crystal. Now, we derive the same conclusions directly from the solution of the Schrödinger equation. We will solve it in the momentum representation. So we write the wave function as equal to summation over k multiplied by a k e raised to power iota k dot r, where the sum is over all k vectors. This restriction on k vectors is needed as wave function must satisfy the periodic boundary condition. In momentum representation, it is also useful to expand the potential in a Fourier series. The crystal potential is a periodic potential with the periodicity of the lattice. Its Fourier series expansion involves only reciprocal lattice vectors. Thus, V r as a function of r is equal to summation over all the reciprocal lattice vectors g Vg into e raised to power I g dot r. Substituting these, one arrives at the following equation. That is summation over k in the bracket, square brackets, we have the kinetic energy h cross square k square by 2m plus summation over g, the potential in reciprocal lattice Vg e raised to power I k dot r minus the eigenvalue. The square bracket closes multiplied by ak e raised to power I k dot r equal to 0. Now we multiply this equation that we have seen in the last slide by e raised to power iota q dot r. Integrate over r and use the property that integral over the entire volume of e raised to power I k minus q dot r is equal to capital omega into delta kq, where capital omega is the volume of the crystal. This enables us to obtain the following equation for the coefficients aq as given by this equation, where this vector quantity minus e into aq plus summation over g Vg a q minus g is equal to 0, where this expression is simply the kinetic energy. Note the Fourier coefficient Vg should also be regarded as the matrix element of the potential energy, that is the expectation value of q plus g, the vector g, where the q denotes the plane wave state. So as you can see from here that it is not simply the q, but it is the bra or the Kerr vector, which is the plane wave state. We can write similar equations for all the coefficients occurring in the previous equation, and it is typically given by the following equation as you can see. The important point to note is that the Fourier expansion of the wave function involves a restricted set of wave vectors. The wave vectors appearing in the coefficient a's of each of the above equations are q and the equivalent points in the entire reciprocal lattice for a two-dimensional lattice. This is a closed set of simultaneous equations among the coefficients a, q minus g, as each equation involves the same set of wave vectors as arguments of the coefficients. These can be written in the matrix form as shown. So this figure, rather the slide actually shows a figure here which tells us about the restricted set of wave vectors. So as we know that the Fourier expansion of the wave function involves a restricted set of wave vectors. The set of vectors which occur in the plane wave expansion of the wave function in the two-dimensional lattice is schematically shown here. The eigenvalues On as a function of q vector from the determinant, and the eigenvectors are some linear combination of the coefficients a, q minus g I. This means that the real space eigenfunctions have the form xi of nqr, which is equal to summation over all the reciprocal lattice vectors g a n q minus g multiplied by e raised to power iota q minus g dot r. Now with some simple manipulations, as you can see that outside the summation we have taken out e raised to power q dot r, we get back the same form as earlier, that is e raised to power q dot r into u and q, where u and q is in the short form we will write it as the summation over g a n q minus g into e raised to power minus iota g dot r, where n denotes the nth eigenvalue and a and q minus g components of the corresponding eigenvector. The previous equation can be regarded as a Fourier series for u and q. Since it contains only the vectors of the reciprocal lattice, it establishes that u and q is a periodic function of the lattice. This is again nothing but the Bloch's theorem, which we have now derived directly from the Schrödinger equation. From this construction of the eigenvalue matrix, it is clear that the eigenvalues and the eigenfunctions for q and q plus g are identical for any reciprocal lattice vector g. Thus, it suffices to take Q from one unit cell of the reciprocal lattice. This is the same conclusion as the one we arrived at from the consideration of eigenvalues of the translational operators. Both the eigenvalues and the eigenfunctions are periodic over the reciprocal lattice. That is, psi n q is equal to psi n q plus g, and O n q is equal to O n q plus g. So students, let us summarize what we have learned in this module. In this module, you have studied 1. How the physical and the chemical properties of solids are ultimately linked to the quantum behavior of electrons. 2. The quantum problem of a single electron in a periodic lattice and the solution of Schrödinger equation using the periodic boundary conditions and the translational symmetry. The concept of Bloch theorem and its physical implication, that is, eigenstates are wave-like and extended throughout the crystal. We have also learned about the Wigner-Zeit cell, allowed number of wave vectors, how the Schrödinger equation can be solved directly in the momentum representation, expanding the potential in Fourier space leading to the same Bloch theorem. And then you also learned about the first billion zone of this simple cubic, the FCC, BCC lattices. Thank you.